Hey, it's Mr. Russell. Let's do some science. Here's my vanadium solution I showed you, my oxidation reduction reaction. It's reacted with some oxygen a little bit, so it's formed a blue-green. It looks blue-green to me, but it may look blue on your screen. But it's blue-green to me, so trust me. If I take it and I add just a little bit of hydrogen peroxide to it and put some, just a little bit in here, a couple of drops. Let's put the stopper on and shake it up, and it should get a little bit lighter. Okay, so it's changing colors. That's great. Just what I expected it to do, and I think you've all seen it before. So let's put a whole lot more in, and it changes some more colors. You may remember from your oxidation reduction reactions that it is the electrons that are doing this, right? It's not really a pH thing, it's not really protons, neutrons, or anything else. It's the electrons and the energy that's coming out of it. That's the point of today's video. The effect that I just showed you can be explained by the photoelectric effect. Einstein studied the photoelectric effect whereby light with sufficient frequency shining on a metal causes current flow. He took a piece of metal and would shine electrons on it. Shine light on it. That light is photons, just like these photons here. And the metal would actually show some kind of current. Even though it was a very small current, it would still show some kind of current. Then the amplitude of the radiation was not important, but the frequency was. So the frequency of the light was what really mattered. It told him that the light must be in particles, each having a given energy. Einstein proposed that electromagnetic radiation can be viewed as a stream of particles called photons. This is what won Albert Einstein the Nobel Prize. And this is his one and only Nobel Prize, was from this one. Nobel Prize. And he was able to, and then he was also able to work with this guy named Max Planck. And Max Planck came up with this equation here, and I showed you before in the previous video that light was quantized, so that we ended up with E equals h nu. H is Planck's constant, and nu is the frequency. It can be rewritten as E equals hc over lambda. The lambda is the wavelength. Lambda is wavelength, and h is Planck's constant, c is the speed of light, and E is the energy. He was able to figure this out because whenever he would shine the light on a certain piece of metal, some colors would be absorbed and some colors would be transmitted. So, and the red light is not absorbed. No, the red light does not have sufficient energy to knock the electrons off the potassium metal. This is the potassium metal here. The green and blue light both can achieve the photoelectric effect, so they are transmitted. And they will emit a photon at a certain velocity here. And since the blue light has more energy, but due to its different wavelength, it will the photon ejected will be at a higher velocity. Notice that this arrow is longer, so that means that it is a higher velocity than the green arrow. There is no arrow with the red electrons because it did not have the sufficient energy to knock it off. Now, this equation right here is what everybody knows Einstein for, and that's E equals mc squared. He's tying energy into matter. And there's actually more to this equation than this. If you look at the really long equation that he came up with, but the most simple one that people understand is E equals mc squared. We'll use this in our nuclear chemistry sometimes if we're trying to, if we're looking at the nucleus, if it changes sizes, or if it decays to a different type of nucleus, then there will be some mass loss and that means that there has to be an equal energy release. So we'll use that eventually, but if there's any loss of mass, then there's a release of energy. If there is an increase in mass, there has to be an absorption of energy. So the debate raged on with the light particles in Einstein's day, and then a little bit later, Louis de Broglie was able to come up with this equation, and he was able to find out that very small particles, like electrons, might also display wave-like properties, and so he came up with the de Broglie equation. He finds that not only does light behave like a wave, but all matter, even electrons, behaves like a wave. So that's really crazy, because if electrons can be waves, that means everything is a wave. All matter, even you, even a baseball, even a ping pong ball, in anything, has wave-like properties. The thing is that whenever we have such huge objects, like things that we can see, you don't actually see that wave. The wave is so small that you don't notice it. But whenever we're talking about something teeny tiny like an electron, we do notice that are able to see a wave-like property. So the equation that he comes up with is wavelength equals Planck's constant, again, divided by mass times velocity. This is similar to E equals hc over lambda. If you know your physics equations well enough and know kinetic energy and potential energy, you know that energy can be put in terms of mass and velocity. So if you play around with the variables enough, you find out that these two equations are actually very similar. This shows a nice little picture just to show that light behaves like a wave up here, but it's also a photon. So it's a particle, it's a packet of energy that moves like a wave. That's how I like to describe it. I'm just reiterating in this slide in words so you can have a chance to write it down, but the de Broglie equation is used to find the wavelength of the particle, and it was determined that matter behaves as though it were moving as a wave. So all matter is behaving as a wave. And then it is important in small objects such as electrons, but is negligible in larger objects like baseballs. So heavy objects have very, very, very short wavelength.